Okay, Assalamualaikum warahmatullahi wabarakatuh. Good morning. Today, I will continue our discussion about the semiconductor diodes. After we discussing about the semiconductor intrinsic and also extrinsic, I will jump to the semiconductor diodes in subchapter 1.6. So, the semiconductor diodes is combination of the p-type semiconductor here and n-type semiconductor here. As you can see that in p-type semiconductor we have majority carrier of hole, and n-type semiconductor we have the majority carrier of electron. So if we connect two kind of the semiconductor without the no applied bias like this one. So there is no applied bias. There is no voltage source between the semiconductor type P and also semiconductor type N. They just connect each other. So the minority carrier in semiconductor type P will go to the junction like this one. So this minority carrier, I mean that this is the electron, so minority carrier of the type P type. And also the minority carrier of N type hole will go to the junction. So the combination of two minority carrier will create the depletion region. So if there is a depletion region, the electron, the majority carrier electron in N-type cannot flow. So it can flow to the P-type, and also the hole cannot flow to N-type. So it's like the isolated resistor. So it's like a resistor. So if we didn't apply any voltage between the P-type and N-type semiconductor. Okay, and it is similar if we applied the voltage of 0. So there is a depletion region here. So there is no current flow from the N-type to P-type, and also the electron can flow from N-type to P-type. Okay, and in this term, to explain the semiconductor diode, we have two carrier flow. The first one is minority carrier here, and another is majority carrier. And if we applied didn't apply any bias voltage here, so the minority carrier, I mean that the minority carrier from the N-type to P-type is whole. So it's like this one. So H is the whole the flow of hole from N-type to P-type, and also IE is also the minority carrier flow from the P-type to N-type. It's like this one, and the majority carrier also this one. So the magnitudes of the minority carrier and majority carrier is similar. So the net current is 0. So if we didn't apply any bias condition in diode, so there is no current flow in the diode. And if we put the reverse bias condition, or VD is lower than 0, so it means that we connect the P-type to negative and N-type to positive like this one. So P-type connect to negative and N-type connect to positive. So this is the reverse bias condition. So the hole in P-type will attract to the negative voltage. This is the hole, and the electron also the electron or negative will attract to the positive voltage over there. So it means that the depletion region between the P-type and N-type become large. So the current is similar to if we didn't apply any bias condition. So there is no current here because the depletion region is very large. So it's like make like a wall, high wall, a larger wall between the p-type and n-type, so the carrier cannot flow from the semiconductor n-type to the p-type or the p-type to n-type. So the majority carrier flow is 0. So we can see from here I majority is 0. And if we put Vd is larger than 0, or we connect the p-type with the positive here and n-type with negative here, so the minority, the whole majority carrier in p-type will go to depletion region because they repel with the positive voltage, and also the electron will go to the junction here because it's repelled to the negative voltage here. So the depletion region will smaller. So if the voltage of VD diode voltage is large enough, so the current will flow from the p-type to n-type, or the electron flow from the majority or n-type to p-type. It's like this one. We have to I majority. It means that the majority carrier flow, and IS is reverse saturation currents. So the ID is I majority, or total the majority carrier flow from the p-type to n-type or n-type to p-type. From type to n-type is hole, and from n-type to p-type is electron, minus reverse saturation current become the ID. ID is the diode current. So if the depletion region very small, so the electron from n-type can flow over the depletion region here. And also the p-type can flow from the p-type to n-type. This is the hole. Okay, through the barrier, so it can be a combination with the electron in the n-type, and the current will flow. So we can see here like the Vd if larger than 0, so the ID is larger than 0. And in ideal diode, the Vd larger than 0 is like in I0 in red line, like this one. So it's like this one. So this is the ideal characteristic of the diode. If Vd is larger than 0, or just a 0, so the current will go to like this one. But there is no ideal diode, so the diode need like specific voltage before they can deliver the current. So we call it Kerney voltage, Vk, or forward voltage, Vf. So it's like in here it's like a silicon. So before 0.547 here, the electron didn't flow. So after the Vd is larger than 0.7, we can see that the current will go like this one. Okay. So how to calculate the diode current? We can use by these equations. ID is Is E Vd per N Vt minus 1. And Is is reverse saturation current. Vd is the applied forward bias voltage. And N is ideally factor. And what is the thermal voltage? Vt is Kt per K. K is Boltzmann constant. T is absolute temperature Kelvin, or operating temperature of the diode. And K is magnitude of electronic charge. This one. Okay, so this is the forward bias conditions. I see that the ID before is I majority minus Is. Okay, so this is the ID I majority here. So because this is very small, Is compared to the I majority, so the ID is become this one. So ID is Is E Vd per N Vt. So if the Vd is positive. Okay, so I skip this one. So, and how about the Zener region? I see that if before that, if we applied the positive bias, like we have the diode like this one, and we apply it, this is n-type and p-type, so this is the positive, like this one. So the current will flow if we put a large enough the VD here. So it's like for silicon is 0.7, the Knife voltage is 0.7 volt, and for germanium is 0.3 volts, and gallium arsenide is 1.2 volts. Before this voltage, so the diode cannot deliver a current. But in Zener region, if we put very large negative voltage here, so it means that if we didn't use the positive bias condition or negative bias condition, it means that I connect like this one. So the p-type to negative and n-type to positive. This is the negative bias. And ideally, in negative bias, there is no current because of the depletion region will be very large. So we can write here. So depletion region will be very large here because the negative voltage is very large. So depletion region very large. But there is a characteristic we can say that this is the Zener region. What is the Zener region? If we applied more negative voltage, so the current will flow, but in opposite direction with the ideal positive current. So here this is the positive, and here the negative. Why there is a phenomenon of Zener? Because the electron can tunneling. Yeah, there is a tunneling electron in the energy in the p-type and n-type, so the electron can can move from the conduction to electron to a valence band without with the very negative energy. So electron can tunneling. So this is the Zener region, and every type of diode has a different Zener region or Zener voltage. Okay, so the Zener region is, we can see that this is the Zener voltage. Okay. Okay. To explain more detail about the Zener region, I will show you this one. Okay. So if we didn't connect to p-type and n-type with any applied bias condition, so in p-type, the Fermi level, the red one is Fermi level. You have studied it in semiconductor device. Will connect each other. This is p-type and this is the n-type. Like this ones connect each other. And if we put more negative, it means that the conduction band of the n-type will, like this one, go lower, and conduction band of p-type will go to higher, like this one. So there is a gap, very small gap between this one, between the this conduction band to the valence band, and electrons here can tunneling from the conduction band to the valence band. If we put very negative energy, so it's become like this one. It's like this one. So this is very thin gap between the conduction band. See, this is the p-type and this is the n-type. So the electron can tunneling electron from the conduction band to valence band. So it becomes the Zener region here. Okay, so this is the Knife voltage, different Knife voltage of the material, and this is the germanium, silicon, and gallium arsenide. We can see that Knife voltage of the germanium is 0.3, Clinic voltage of silicon is 0.7, and Clinic voltage of gallium arsenide is 1.2. It means that in germanium diode, if we applied a bias condition lower than 0.3, the diode cannot deliver a current. And in silicon, so the bias voltage must be 0.7 or higher than 0.7, and also the gallium arsenide is 1.2. The limitation is 1.2. And if we increase the temperature, the Clinic voltage will like this one, increase temperature. And if we decrease the temperature, Clinic voltage also will go to another way. And this is the ideal ferrous practical of semiconductor diode. So this is the actual characteristic of the silicons. So we can calculate the RF. RF is the resistivity of the diode. So RF is VD per IDE, just like this one. In short equivalent circuit, VD is 0. So if VD is 0, so the current is 5. So we can get that this is a short circuit equivalent, or RF is become 0. And if in the reverse conditions, if the VD is very high but negative condition, ID is 0, there's no current. So the resistivity of the diode will be very high, or like open circuit equivalent. And how to calculate the resistance level? We have three kind of the resistance. The first one is DC. DC is by simple equation. To calculate the static resistance or DC, just put in the graphic the diode characteristic like this one. Put one node in the graphic, and then we go to this one. This is the VD here, and this is the ID here. So we can calculate the RD. And for AC, we have to put two different point here. It's like we did this point and this point, and here maybe this point and this point. And then we put this calculation, delta VD per delta ID is the AC resistance. And by this is, if we make analysis of the AC by using this calculation, we can get that for the AC, RD is 26 millivolt per ID. Okay, and this is the average IC resistance. By using the graphic, we put two nodes here, and then we calculate the average resistance by delta VD per delta ID. And then this is the diode equivalent circuit. The first one, this is the piecewise linear equivalent circuits. I mean that this is like actual. This is the diode, and we draw a model of this characteristic by piecewise. So we can draw the diode like this one. So it's like Vk is 0.7, and then we have a resistor or resistivity REF 10 ohm. And then this is simplified equivalent circuit. We imagine that REF is like a closed circuit, so REF is become 0. So Vk is 0.7. It's like so, like this one. So in simplified equivalent circuit, we didn't apply any resistor here because we assume that REF is 0. REF 0 is like a closed circuit. Okay. So if we draw, this is another simplified of the diode, and this is the ideal equivalent circuit. There is no Vk. So after the Vd is 0, so it become very high currents. So this is the summary. This is for this DC resistance and AC resistance, and this is the average IC resistance. And this is the in diode, because between the p-type and n-type we have the depletion region. So it's like the capacitance. So this is the diode n-type and p-type, and we have, if we connect each other, so there is a depletion region here. This is the depletion region. And p-type, the magnetic carrier is positive, right? And n-type magnetic carrier is negative. So it's like we zero capacitor here. This is the positive and negative, and this is the isolator. So it means that diode is like the capacitor. So there is two kind of capacitor in capacitive in diode. The first one is reverse bias region, or the transition or depletion region, or CT, and another is forward bias region, and we have the division capacitance, or CD, or storage capacitance. So in CD, this is the forward bias region. So it will be happen in the forward voltage, and CT, or depletion region capacitance will be happen in negative voltage, or in reverse voltage. Okay, and another is reverse recovery time. So it means that from the forward to reverse, if we turn off the diode, or if the first we connect the diode to the bias condition, and we remove the bias condition, so the current didn't directly make a transition between the forwards on to off, but they need some time, some specific time. It's like the transition reverse recovery time. So this is the TRR, or reverse recovery time. So reverse recovery time is consists of two, TS and TT here. TS is storage time, and TT is TT is time from the storage time until the diode off, like this one. So the TS per TT is become TRR. Okay, so this is the diode specification sheets. If you want to use the diode, so you can first check the diode specification sheets, like this one, and you can determine this is the forward voltage, or VK, okay, connect voltage, and then you can determine the PD max. PD max is VD.ID. VD is the diode voltage, and ID is a diode current. And also you can see that this is the breakdown voltage here, and capacitance, and TRR, or reverse recovery time. And also you can see some graphic in the data specification sheets, like this one. This is the power dissipation. We can see that in room temperature, the power dissipation is very high. It's like 500 milliwatt from this diode. Each diode has the own characteristic. So if we increase the ambient temperature, the power dissipation will be lower, like this one. Okay, so this is the another discussion, the diode diode notation. Maybe you can see like this one also in the lab. Okay, so I think this is all. This is the Zener diode I explained before. Okay, I think this is enough from the semiconductor diode, and see you in next chapter, semiconductor circuits, semiconductor diode application. Sorry. Okay, good morning. See you next time. Assalamualaikum warahmatullahi wabarakatuh.